Here we go. What conditional convergence is an easier convergence standard to meet that's applicable to alternating series. So, what are the three conditions for conditional? Actually, never mind, that's part B. Let's do part A. How do you show absolute convergence? The absolute value. You say if you took the absolute value of the terms and removed the negative, what would happen? In this case, if we remove the negative, you get the series 1 over n to the 3 halves, which converges in P series, yes, converges T series with P equal 3 halves greater than 1. So in terms of the question, does it absolutely converge? Yes, the alternating series absolutely converges. Okay? Part B, then, is the condition. What are the three conditions you need to meet for alternating series convergence conditionally? Alternating, you have to start by first of all saying, this is that special case of an alternating series. Alternating. What's the next condition, or a next condition? They don't have to be in order. Yeah, you have to show that the terms are decreasing. Now, in this case, then, we could start by saying n plus 1 is most definitely greater than n. N plus 1 to the 3 halves is most definitely still greater than n to the 3 halves. In other words, if I took the 3 halves of both sides, it would still be true. And then 1 over. Yes, ma'am?
What if you didn't do the n plus 1 greater than n? Like you just made
You started here?
Yeah.
I'm okay. Okay. So, did we not therefore just show that the n plus 1 term for a next term is less than the one before it? Yes? That's condition 2. And then the third condition is that the terms go to 0. They have to go to 0 or past divergence term to even have a chance. All right? Now, because those three are met, we would say the series conditionally converges. It's a hypothesis kind of theorem. If it's alternating and this happens, then it conditionally converges. So we showed those three happens, so we can conclude conditionally converges. All right? Now then, here we go. Today's lesson is a humdinger. It builds off of this. So, all right, you can show it conditionally converges. Now, estimate the sum. Now, we have very rare cases where we can find the exact sum. Give me a case where you can find the exact inference. What's one more? Telescope. Yeah, all right. Now, mostly those series don't have a formula. And the best you're going to do is approximate. Now, approximation is a big idea of calculus, yes? Give me, within 30 seconds, give me 10 ways to estimate, or estimation is done in calculus. Trapezoids, rectangles, should we go left, right, or midpoint? What? Euler's method, Euler's method. Euler's method, got that? How about a secant line to estimate a tangent slope? How about a tangent line to estimate a function value? Differentials to estimate? That actually goes with trapezoid errors, but that's yeah. Seems like I have at least one. That's right. Let's go there. Okay. Now, just like trapezoids, as Alyssa mentioned, after we use trapezoids, thank you. Anytime you use an estimation method, the next logical question is, okay, I have this estimate. Now you want to know what? How good is it? Is my estimate any good or not? How far off? Now, do you ever really know the error in your estimate? This is like teaching junior high. I look out at you, I have 3 eyeballs on me and the rest of So let's try again. Is it ever really the case that you know how much error you have? No, because if you knew how much error you had, then you would actually know the answer. You wouldn't estimate it at all. You would know the exact answer, right? So you never really say, hey, my error is this. Instead, you say, I know my error must be less than this. So you work with an error bound, not the error itself. You say, I know my error must be less than this. Now in a trapezoid, you consider how concave it is and how many trapezoids, and you can bound your error. Today, you'll be bounding your partial sum estimate with a really slick, this is so cool, and it's really easy too. So you're going to love it. All right.
Why should I call humdinger?
It is a humdinger.
You just listened to the word. You said it was.
It is. It's easy and a humdinger. It can be both. Okay, but I usually use humdinger for this is going to be hard. Watch out. But this is just cool. Okay. Now, you're going to love it. You're going to think, wow, that's what you're going to think. All right? Give me the first 7 terms of that alternating harmonic series, please. Try again. Negative 1. 1 half. Negative 1/3. Okay, now obviously that goes on forever. And did you know that on the AP test, once we get there, if you fail for ... in certain places, you will lose points. It's infinite. Okay, so get in the habit of showing infinite when it's infinite. Now, I actually asked for the first 7 terms, so you would be, so, now, give me the first 5 partial sums. What's S1? Negative 1. What's S2? Negative 1 half. S3, now wouldn't it be S2 plus the next term being added? So negative 1 half minus a third, and that is negative 5/6. Sum 4 would be the sum of the first 3, so negative 5/6 plus A4, which is 1/4. What is it? Negative 10/12 plus 3/12, so negative 7/12. Do you agree? S5 would be the previous terms plus the next term. What's the next term? Negative 1/5 is the next term. That's negative 35/60 minus 12/60. So negative 47/60. Okay. So in order to graph these effectively, somebody have a calculator in front of them? Hey, would you tell me what negative 7/12 is roughly to 2? 5/8. Okay. I don't care if you round or truncate. What about 47/60? I imagine just below 7/8. Okay. Okay. Now, for the interest of heading to where we're going to head, would you please graph the partial sums? The least is negative 1, so if you just make a scale of 0 to negative 1, you should be good. The first partial sum is negative 1. The second partial sum is negative 1/2. The third partial sum is about negative 0.8. The fourth partial sum is about negative 0.58. And the fifth partial sum is about negative 0.78. Okay. Now then, because this conditionally converges, we're seeing that spiraling in towards the true sum, yeah? If I asked you to place the true sum, ballpark estimate, where would it be? 0.68 seems reasonable. Somewhere between 0.58 and 0.70, where we left off, I'm thinking somewhere in the 0.68 range seems reasonable. Okay, call this. Now let's label these, please, for the sake of making these good notes. This is S1. This is S2. This is S3. This is S4. This is S5, and this is, I guess you could say, S infinite if you were to put a subscript to it, but we don't. You just call it S. S is the true infinite sum. All right? You with me? Okay. Look at the pattern to the belows and aboves. It seems like the true infinite sum is always above the ones that are odd. Why would that be? Given that the terms look like this. Why would the odd ones be too low. Yeah, they're too negative, really. They end in a negative every time. And so you're ending with the last negative and you're neglecting some of the terms afterwards. And so the evens end at a positive, and so it makes sense that there may be a little too high. The true sum is somewhere between the evens and the odds, right? Right? If we were to say this in a really long inequality way, string of inequalities, what's the least of all those? S1 is the least. The next least is S3, then S5, then okay, S7, yes, but I mean as far as the ones we have, the true S, the true infinite S then is above those odds, but it then would be less than S4 and 2. S2 is the greatest of the bunch, yes? I'm just looking vertically as I go. Really? Okay. Now then, the beauty of this is so cool, man. Mathematicians blow my mind. Check this out. Our goal for the day is to analyze how much error we have by using a partial sum to approximate the true sum. Let's start there. Just not that it's not obvious, but why do we have error at all if I use a partial sum? Yeah, I'm using a finite number of terms to estimate a sum that's infinite. So the minute I leave off some, I'm going to have error, right? Okay, so it stands to reason we have error. Let's talk about how we can kind of bracket that error. How much error? Let's focus just on S1, 2, and the true sum. I think you'll agree that S1 is less than S, which is less than S2. Okay, can we all agree on that? Okay, now let's talk error here. We need to get error involved. Now say I wanted the error in S1. What's an expression for the error in S1? Error is how much off we are from the true sum. How much off? What math operation does that imply? We want to know what the difference is between the two. So what's the difference between our partial and the true? So that means subtract. I need to get S minus S1, the difference between the partial sum and the true sum. That's the error, right? All right. Now combine these two ideas. If I want S minus S1, then, well, here's a bunch of S minus S1. Couldn't I get S minus S1 in here if I just take every one of these and subtract S1? So I'm going to take this, what I had, and S is less than S, or S1 is less than S, which is less than S2, and I'm going to subtract S1 from every one. Now, is that okay mathematically? Did I break math there, or is that allowed? That's allowed. I'm subtracting the same thing from all three parts, so inequality should be maintained. Okay? Now then, simplifying. S1 minus S1 is 0. S minus S1 is S minus S1, but it represents the error in using only one term. And S2 minus S1. What is it? 4. Okay. What is S1 is the sum of the first one term, right? S2 is the sum of the first two terms. So if I took the first two terms, subtracted away the first one term, I would be left with the second term. What is it? A2. The error must be less than the next term. Okay, and that is the error in using one term must be less than just the next term. S minus S1 is just less than, so what is it less than? If I use, actually, what is S1? What's S1? -1. It has to, the error in that is an approximation. It has to be less than A2. What's A2? Or the absolute value of A2, really. 1/2, okay? Now I'll talk absolute value in a second. But that actually makes sense. It seems like the difference here between S1 and the true sum is less than 1/2 because there is 1/2, and there has to be less than, yeah? All right, now, skip S2 for a second because you got a little negative action in there that makes it a little more complicated. And let's go to S3. Say I wanted to talk the error bound or the error for S3. I know that S3 is less than the true sum because those odd numbered ones are less than the true sum. And that's less than the true sum, and that's less than, I'm going to use S4. Obviously, it's less than S than a lot of things, but I'm going to use S4. Cool? Okay, now if I want to talk error bound for S3, then that means the difference between the true sum and S3. You want to bound that. So to get S minus S3, I'm going to take that inequality and do what? Subtract S3 from each side. S3 minus S3 is less than S minus S3, which is less than S4 minus S3. Now that then results in 0 is less than the error, S minus S3, which is less than 4 minus S3, or A4. The first 4 terms, take away the first 3 terms, leaves you the fourth. Must be less than the fourth term. Now, so that again, the same conclusion. The sum of error in the sum of 3 is less than the fourth term, or the next term, generally speaking. Okay? Now, just for the sake of rigorous proof, I just want you to see the negative side. The negatives involve a little bit of monkey business. I went straight from S1 to S3, but let's say we looked at S2. Okay, I know that S2 is actually greater than the true sum, and that's greater than S3, yeah? Do you agree with that? Okay. Now,
Pick 3.
good question. I want to get into the next term. You'll see, and so
That's okay.
that's why.
If you pick S1, it's exactly the same as what we did above.
Yeah, exactly. Okay, so it's with a direction in mind. So if you want the error in S2, then what do we need to do? Error in S2 is the difference between the true sum S and S2. So I want to subtract S2. So I'm going to subtract S2. S2 minus S2 is greater than S minus S2. It's greater than S3 minus S2. Now the problem then is that you have to do a little bit of, have some good solid math skill in inequalities and absolute value. This here. Okay. Now S minus S2 is less than 0 is what this is implying. Do you agree that that's what this is saying? Now that actually makes sense because if I take S and subtract away S2, which is larger, I would get a negative. So that seems reasonable. Same goes with S3 minus S2. That's a smaller number, larger minus a larger number. That also would be negative. So that's cool. Now the deal is this, though. On error, we don't care about direction. And so as far as above or below, I don't care. Direction doesn't really matter. I want to know how off it is, not which direction in this case. Sometimes you do. So we're going to take the absolute value. Now, here's the thing though. Be careful. Imagine if I had negatives in an inequality. Do you agree that's true? 0 is greater than negative 2? And do you agree that negative 2 is greater than negative 3? Do you agree with that? Okay. When you throw the absolute value, then absolute value of 0, absolute value of negative 2, absolute value of negative 3. What happens to the inequality? They have to switch. Okay. So when you use absolute value, you're talking about the magnitude of the number itself without losing the sign, so you must switch the inequalities. So now, when I want to say, all right, I don't care about the direction of the sign of my error here and here. I just want to know how much error. I'm going to throw absolute value on. But when I throw absolute value on, I use a switching of the inequalities. Now that said then, my error will be less than S3 minus S2. Well, what's 3 terms? Take away 2. I take the sum of the first 3 terms, remove the first 2 terms, I get the third term. All right, now then that is, it shows basically that it works either direction, even, odd, it doesn't matter. The sum, the error in any partial sum is always less than or equal to, actually, for cases we'll talk about later, the next term. So if, now this, by the way, if this is a series that conditionally converges, okay, why is this necessary? Why must it conditionally converge? Well, if it doesn't conditionally converge, then what's S? It's infinitely large, I assume. Okay, infinitely large. You with me? Now, can you imagine then using a finite sum to estimate something that's infinite? How much off are you going to be? A lot. In fact, infinitely many. Can you bound an error that's infinitely large? No. Okay, you're trying to estimate something that's infinite with something finite, and then you're trying to say the error in that crap is going to be also finite. That's just crazy talk in 2 levels, all right? So it's got to converge in order for any of this to hold true. You have to then, first of all, show it converges so that this idea can be used. This is what the problems look like. Here we go. Actually, quite a variety. So, using the same series, which is to say the alternating harmonic, and that's the word. Okay. Show the error in S6, sorry I didn't use a subscript there, is less than 1/5. Now there's nothing special about 1/5, it's arbitrary. This happens a lot on the AP test. There's no meaning to it. It's just a number I can be sure to show. So this is what must first be done. You must show that it conditionally converges. And it doesn't have to be super rigorous. Okay, the start of the show is the error count. You just have to really be sure that it converges before you do anything, but then you proceed. So, is this an alternating series? Check. Wouldn't you agree that the terms go to 0? Yes? Do you agree? I don't want to force you. If you disagree, let me know. Do you agree? Okay. And in terms of the terms decreasing, n plus 1 is greater than n, so 1 over n plus 1 is less than 1 over n. So does it appear that the terms decrease in absolute value? If we were to remove the sign element, do the terms decrease in absolute value? Yes, they do. Okay? All right. You'll see happens once in a while when we get to the AP test prep, you'll see sometimes you just will say that all in one sentence. This is an alternating series whose terms decrease in absolute value to 0. And you just say that all just like that. But we'll get there. Now, because that's true, we could therefore say that it must be the case that the difference between the true infinite sum and a 6-term partial will be less than or equal to the 7th term. Well, the 7th term I can find. What is the 7th term? 1/7. And isn't that less than 1/5? Well, surely our error is less than a 7, which is 1/7, and that's less than a 5th, so our error must be less than a 5th. So I use errors.
Wait, so that's it?
That's it. It didn't say find S6. It just said show the error if you were to find S6 would be less than a 5th, and it is. If I were to find S6, it would be less than 1/5 off. In fact, it would be less than 1/7 off. Okay? You try. Go. This, by the way, if sometimes you think, I don't know if this is a big thing or if this is a little thing. This is a really big thing. So get good at it now. you see that started at 2, yeah?
I saw it.
Oh, I never even found S4. This one did ask me to find S4. Stupid me. Sorry.
Yeah, it is. I read it. Negative.
So if I start at 2, I start -1/2. 1/2 plus 1/6 minus 1/24 plus 120. -60 plus 20 minus, I got that 5 plus 1, 21 minus 65. Did you get -44 1/20ths for an estimate? Or no? Feels like it's good. -11/30ths?
That's right.
Yes.
Why would you put dots after the S4?
You're right, you wouldn't. Good point. All right. Sorry, I should have started with the sum. The S4 sum is -11/30ths. Do you agree? Okay. In terms of the series, it conditionally converges because it's alternating. The terms go to 0 and the terms decrease. And so I can be sure that this error bound idea is applicable. S minus S4 is less than or equal to A5. What's A5, or the next term in the sequence? With absolute value, 1/6 factorial, which is 1/720, which is that less than 1/500? It is. Factorials are a little bit like times tables or exponents and powers and stuff. You probably want to about 6 factorial memorized. So 2 factorials 2, 3 factorials 6, 4 factorials 24, 5 factorials 120, and 6 factorials 720. You'll want to get that. Okay. Are you with me so far?
Wait. I feel like it. Why is it not -1? Oh, is it because you just did the absolute value?
Yeah, you always use the absolute value. Your error, we only focus on positives. Okay? Okay, now it's a lot like trapezoids. Sometimes after, hey, you estimated how much error, they then said, how many trapezoids would you have to do in order to get error less than this? Remember those? You often have that kind of question here. How many terms would you need to include before you had the error less than some benchmark? Okay? So let's try a few of these. These are going to be necessary for a lot of Taylor series problems. So, how many terms necessary to get error less than 120,000? Pretty soon, in about a week, you're going to be estimating the cosine of 2 radians. No calculator. Nope, serious, no calculator. And I'll say with error less than 1 to 200,000. And you'll have to say, I'll need this many terms in order to get that. Okay? So, this is what your calculator does to get that. All right? So, the series, -1 to the n plus 1 over n factorial, is started at 2, yes? We need, how many terms necessary to get less than 1/20,000th off? Now, we know it converges and all that stuff has been met. So let's just say the question is, I need to find n so that the partial sum through that many terms will be less than the next term, which is n plus 1, and that then, if that's less than 1/20,000, if I can find a term that's less than 1/20,000, then the error would also have to be, as a consequence, less than 1/20,000, right? So now let's focus on this. What is the n plus 1th, an expression for the n plus 1th term? Absolute value. I don't care about that.
1 over.
Yeah, all right. So here's the 1 over n plus 1 factorial. So less than 1/20,000. Okay, do you agree that's what that implies, Jay? Now, normally I would then say, okay, use my algebra to solve for it. When you use algebra, though, you use inverse operations. Well, what's the inverse of factorial? It does not have an inverse operation. Okay, unfactorial. Divide by the same thing. That actually would make sense, but no. So this factorial has no inverse. So it is trial and error.
Oh, no.
Boo-hoo. You got a freaking calculator. Jeez Louise.
You know, I got a calculator.
Okay? No, you don't even need a calculator.
Yeah, we do.
No, you don't. 1 over 6 factorial is 1 over 720. 1 over 7 factorial is that times 7. 49,000 plus 140, so 4,900, excuse me, 4,900 plus 140 is 1 over 5,040, yeah? So what's 1 over 8 factorial? You don't need it exactly, but it would be 1 over 40,000-ish, yes?
You're right.
Do you agree? 1,000-ish? 5,000 times 8 is 40,000? It's, I don't care what it is exactly, I just need to find the first one that's less than that. So I'm done, I'm good, okay? Okay, so it looks like I need n to equal 7. Okay? N to equal 7, so I would need the sum of the first n terms. Okay. All right. Try one on your own. Would you actually, I'll just, in the interest of saving you some time, because you're a bunch of sissy crybabies, would you assume I'll just tell you this converges conditionally? So you don't have to, actually, you maybe need to practice to that.
No, we should just practice one.
Do this one first.
First, so you're saying there's a chance.
Maybe there's a chance. Did we talk about there's a test tomorrow?
No.
No. There's a test tomorrow. The test to review, I'll do this first, then we'll talk about the test.
It didn't happen. Wait, what lesson is it through?
36.
36.
Piecewise is 37, so it's fundamental theorem part 2, 36.
So not 37.
Not 37.
Good, I hate that.
37 is piecewise integration.
Oh, I do hate that one, so yeah.
Oh.
I knew it.
Yes.
Do we have to write like 5 ends so that?
No, that's just for note purposes, but it might be nice to communicate your thought process.
You didn't assume the other one was through.
If you want, we can show conditional convergence. I just was trying to save you a little. You may use a calculator.
Wait.
Thinking it'll need to be at least 10 in order to, I mean, 400 is a pretty big starting number, so the exponential has to get up there a little before it passes it, I would think. 4,000, 2 to the 11th, is that 4,000?
The 11th is like far over.
No.
I need to say more.
11 is
11 does not work.
12.
Wait, question mark.
Okay, so what that's 5,200 and 2 to the 13th is 8,192. Now, I suppose besides trial and error, we could graph these and find intersections and stuff too. Analytically, it's probably not going to happen in linear exponential combination. But so I'm thinking n equal 12. So to answer the question, how many terms required? We would need 12 terms. Fala?
Wait, how come the one above it says you put S7?
Oh, the question was how many terms required, so that's n. You're right. I should have said n equals 7. Okay. All right. Questions on, actually, a couple things. The test, first of all, the test is through 136. The review will be, and the key will be online after school, probably after 4:30 or so. And that's good. I would like you to have your homework quiz back so you can see if you understand pretty well or you're really clueless. I'll give you a copy so you know what you're doing.
That's not 138.
Yeah, right here, that you can take that as a sign that you understand things pretty well. If you did badly here, you just take it as a sign that you better review a little bit.
Oh, I got 18. It kind of goes like soup. It goes that way, and this is just kind of that's like they're off. You have to.
Yeah, 148.
That's the better.
Yeah, I mean, we have it right here, so whatever.
So, yeah, I must have there. I just get like down here, but like not
So on this first.
If you're at about 10 out of 16 or above, you have a pretty good idea. If you're in the 14, 15, 16 range, you have a very good idea.
Oh, not bad. Third.
Okay. All right. You should definitely go over those. You might see those again. All right. Questions on 138? One. What else? 18? 118. Did somebody say 2?
Oh, 19. 19. Oh, 18. Oh, that's already
19. 118, 219. Okay.
I had a question.
15? Okay. 14. Okie dokie. Here we go. 138, number 1 is right here in front of you. Will you let me get your copy of this? Okay, now, one might make a little more sense. You might have seen his craftiness trying to get you ready for today's lesson in this question. Now, 1/2 to the end. Prove it converges. This converges because, you might play with this a little bit to make it more geometric. Do you agree that in order to put that negative and this together, you can either expand some terms or you might put them together by saying this is -1 to the n, -1 to the first, times 1/2 to the n. When they have the same exponent, then you could put them together into a single Oops. Like that. Okay? Now then, if you can look at that, then you can see that this is geometric with an R of 1/2. Okay, so that's pretty easy to prove. I guess you could get fancy and prove some other stuff, but that's the easiest way to go. Yep.
If we just, synthetic converges absolutely, and then.
Sure. Oh, sure, absolutely. Yeah, that works. Yeah. Good. Yes, absolutely. Find the value of the series. Because this series is geometric converging, it follows this formula. Be careful with A1. Just make sure you identify the first term properly. A1 is positive 1/2, yes? And the common ratio is negative 1/2. So the true infinite sum would go to 1/3. C then is where they're starting to lay the groundwork for today's lesson. How does S4 compare to the sum? Let's find S4 first. It is 1/2 minus 1/4 plus 1/8 minus 16th. That is 8 minus 4 plus 2 minus 1, or 10 minus 5, 5/16. You could say, how is it? This is kind of ambiguous. What do you mean, how does it compare? Well, I guess, I don't know. I guess in looking at what they're hoping for, I think they're thinking the error is 1/3 minus 5/16, or 16/48 minus 15/48, or 1/48. At that point, it's 1/48 off. How does S4 compare to A5? A5 is 1/32. The error, 1/48, is less than A5, 1/32. Now, I knew all to do that stuff because I taught this book before, and the alternating series are bound. In terms of should you have known that, no. The question was way too ambiguous for you to have known that's what they wanted you to do. So don't sweat that. Okay? As long as you understand that. You with me? Okay. 18. 18, 0 to 4, x squared minus 4. I was pleased. I was happy with how a few people on the quiz mindlessly plowed ahead without seeing a discontinuity. So good job in that respect, seeing the discontinuity and not just saying, hey, here I go.
You were happy that they...
How few people get Did I say that wrong?
You said it right.
Very few people just said, here I go integrating, and never even saw the limit to the discontinuity.
I get it.
So, the limit as to negative, it goes like this. So, I'm thinking the limit as a goes to 2 from below, from 0 to a. And the limit as b goes to 2 from above. B to 4. Okay. Shall we continue? Shall I continue with this? Okay. Does anybody have the partial fraction decomposition? Please. So something over x plus 2 and something over x plus 2.
Over x plus 2 is negative 1/4. And then the other one's 1/4.
Thank you.
I feel like it's so. Oh, I thought you were. I just forgot that it's very good.
Okay, when you see logs, you should be wary because it could combine.
Logs, you should be wary.
Yes. X plus 2 plus 1/4 log of x minus 2 from 0 to a.
Oh, keep that.
Yeah.
Phew. Okay, are you with me?
I'm just gonna write C.
Okay, you definitely want to put these two together into a single log. So that would be the log of the fourth root of x minus 2 over x plus 2. Same deal here, the log of the fourth root of x minus 2 over x plus 2. We. Okay. Evaluating. Almost. The limit as a goes to 2 from above. Natural log of the fourth root of a minus 2 over a plus 2 minus log of.
Wait, B approaches. Why are they both approaching them to minus?
Say what?
B should be approaching to the right.
Yes, you're right. Thank you. Hey. So I'm thinking I have a problem here at 0, do I not? Oh, it's the absolute value. Okay. So the log of 1 plus the limit as b goes to 2 above of natural log of 4 minus 2
At some point in the near future,
over 4 plus 2
a lot of people you can chase in this class.
minus log of fourth root of b minus 2 over b plus 2. You're welcome. Have a great day. This is a humdinger. Okay. As a goes to 2 from above, this goes to the log of approaching 0. Log of approaching 0. Log of approaching 0 is negative infinity minus 0
Oh my god, that's long.
plus the limit as it's almost done. The log of
Wait, can't you just go right there and say, oh,
it's diverging.
It's diverges, which I don't.
Okay. Diverges.
that is such a, I don't like those, because they like always diverge.
Well, just without
No agreement with the financial office?
Okay.
Wait, no.
No. That was a humdinger. I wonder. I guess they did ask, but I just didn't get to that question.
It's
Strangers and